Oh, hello. Welcome to Science Sundays. I'm John Beacom, your host for today. Science Sundays is one of the premier outreach events of Ohio State's College of Arts and Sciences. We bring you cutting-edge science presented by outstanding speakers. Normally, we also bring you cookies, but today we're online only, so I hope you can find a cookie in the pantry. Why is Science Sunday so important? It brings you the excitement of discovery. It encourages scientific thinking, and it nurtures a community of like-minded people. Today's talk is far away from today's concerns, and it's a mystery from outer space. A mystery that took decades to solve, and one that still has us physicists and astronomers scratching our heads over the details. Our guest today is Professor John Horack, the Neil Armstrong Professor of Aerospace Policy in the College of Engineering and the John Glenn School of Public Affairs. Professor Horack is also the Senior Associate Dean in the College of Engineering. He has had a long and distinguished career spanning government, academia, and business. Normally after the talk, we have about 10 minutes of formal questions, followed by an hour of informal discussion at the reception, with cookies. But today, because we're online only, what we'll do is we'll let the question period happen online for as long as people would like. With that, let's welcome Professor Horack. Thank you.
Good afternoon and welcome to the first technology-enabled edition of Science Sundays. My name is John Horack, H-O-R-A-C-K is how you spell it. I am the Neil Armstrong Chair in Aerospace Policy here at Ohio State, which is an appointment that is shared between the College of Engineering and the John Glenn College of Public Affairs. I teach rocket propulsion and orbital mechanics in mechanical and aerospace engineering, and I teach leadership courses, for example, in the John Glenn College. I also serve as the Senior Associate Dean of Engineering. I'm really happy to be with you today. Today's April 5th, 2020. It's the anniversary of the launch of the spacecraft that you see behind me, a spacecraft called the Compton Gamma Ray Observatory that was launched in 1991 on the space shuttle Atlantis. And really proud to have been a part of that. And what we're going to talk about today and what I hope to share is some of the mystery of the universe that was unraveled in part using this spacecraft, a mystery that surrounds a phenomenon known as gamma ray bursts, the most powerful explosions anywhere in the universe. And what I thought we would do is just share a little bit of discussion today. I will try to keep the mathematics down so that it's as accessible as possible. But for those of you who are mathematically inclined, I'll go ahead and also have some math for you. So here on the screen, I think you see the launch of the Gamma Ray Observatory, April 5th, 1991. Space Shuttle Atlantis, about, I don't know, 9:15, 10 after 9 in the morning. It had been a terribly rainy night the night before. Didn't think we were going to get off the ground. And then also in the lower right-hand side, you see Jay Apt and Jerry Ross in the payload bay of Atlantis during the deployment of the spacecraft. 34,000 pound, 17-ton satellite, the heaviest science payload ever launched from the space shuttle, flew for a total of 10 years. And its purpose was partly one of the 4 instruments. The purpose was to explore this phenomena that we're going to talk about today. But the phenomena didn't start in 1991. In fact, like many things that deal with astronomy, astrophysics, and the spaceflight program, there's a deep tie to history, a deep tie to the United States national security enterprise. And one of the things that right before I was born, I'm a 1965 model human. The Cold War had started following World War II, and you see on the left President John F. Kennedy addressing what I think is the speech that he made at Rice Stadium in Texas. And then on the right-hand side, you see Nikita Khrushchev at the UN pounding his shoe on the podium, and in the middle, a thermonuclear weapon. And for those of you that did not live through the Cold War or have no recollection of the Cold War, it's pretty hard to describe just how tense that time really was. And I came late to the Cold War, born in 1965, and so I don't remember all of it. But this was a time of tremendous acceleration in the weaponry that the United States and other nations around the globe were able to build. And it became pretty obvious that we weren't doing ourselves any favors by testing these nuclear weapons in the atmosphere, blowing up, islands in the Pacific. And so in October of 1963, the United States Senate ratified a treaty called the Partial Test Ban Treaty. And this treaty was also signed by the United Kingdom and, at the time, the Soviet Union, the USSR, the three nations that had substantive thermonuclear weapons capability. And this treaty was designed to limit the testing of nuclear weapons in the atmosphere, in space, and underwater. And it sent a lot of the testing that we did underground. And it was a very, very good thing, especially for cutting back on the proliferation of nuclear weapons, as well as protection of the Earth's environment, because these things are not benign devices when they're set off. They create all kinds of environmental problems. And one thing about a treaty is not only do you have to ratify it in the United States through the Senate, the president can negotiate the treaty, the Senate has to ratify it in order for it to become in effect, but you also want to be able to verify. And you want to be able to verify that other signatories to the treaty are not violating it. And so there was a classified satellite program called Project Vela, which was one of the US means of verifying compliance with the Partial Test Ban Treaty and monitoring for these clandestine nuclear tests that could be done in space or in the upper atmosphere, perhaps even behind the moon. You need a way to make sure that the other signatories to the treaty are going to comply. Now, you may not want your other signatories to know that you can tell if they're going to violate the treaty. So this Vela program was classified. There were 12 satellites. You see a picture here of what the satellite looks like, and on the right-hand side, you kind of get an idea. It looks actually like kind of like a three-dimensional Chrysler logo, maybe 4.5 foot diameter satellite. There were 12 of them in all. They were built by a company called TRW. Thomson, Ramo, Woolridge are the names of the founders of that company, and it's a company that had a history in Ohio and Cleveland in automotive, but also in aerospace in Southern California. These satellites were built later. TRW would build the high energy astronomy observatories, the Gamma Ray Observatory that I showed you in the first slide, Chandra X-ray Observatory, and lots of other things. But these satellites were built and then they were lofted in pairs. And they were put into very, very high orbits around the Earth, 70,000 mile orbits. Geostationary satellites orbit at about 22 or 23,000 miles. The moon is about 250,000 miles. So you can see that these satellites were almost sort of a third of the way to the moon. Very, very far from Earth, and there's a reason for that we'll talk about. And each of them, not very big, you can see they're small, but they carried a host of X-ray, gamma ray, and neutron detectors, looking for the kinds of things that you would expect to see if someone, an adversary, were to test or detonate a test nuclear weapon anywhere in space. Now you can see that spacecraft is pretty small. It's not a lot of size to collect the information, collect the gamma rays or the X-rays that would come. Also, you have to have satellites that are lightweight, because even weight is a premium when you try to fly a satellite in space. So these detectors were not all that sensitive. They were of limited sensitivity, and they were designed to search for human-induced events. And so they were launched throughout the 1960s. You can see the liftoff here. This is a Titan launch vehicle. That's a pretty beefy launch vehicle to send a spacecraft into orbit. But of course, because you're going such a great distance from the Earth, you need a pretty mighty rocket to make that happen. So we put up our satellites, we put up the Vela network. Coincidentally, one of the leaders of this program was a man named General Jim Abramson, Air Force general, who later on wound up being the head of the first Strategic Defense Initiative, and also was with President Reagan when he went to Iceland to negotiate nuclear proliferation limits with Mikhail Gorbachev. So, and General Abramson is still around today and has some very fun stories to tell about his time, not only managing Vela, but his entire career in the national security space enterprise. So we put up the satellites, and lo and behold, there were these events. What I've got here on the right-hand side is a plot. You can think of it as sort of a Geiger counter. So this is This axis here is sort of how bright is something in the detector, sort of. So if you see a signal that goes like this, you know the detector is seeing something. And then here is time. So 0 seconds, 2 seconds, 4 seconds, 6 seconds, 8 seconds. So 2-second increments. And what you can see is that this is the gamma ray level in the detector. It's not a picture, but it's a counter, if you will, or sort of a seismograph or a Geiger counter. And you can see there is a natural level of background radiation that occurs in space. And then very, very quickly, boom, almost 1,500 counts per second in that detector. And that you can also see that the signal is quite variable and then sort of decays away here in what could be, I don't know, some kind of exponential decay or exponential-like decay. And this is pretty unusual to see in a detector that you put up looking for human events. Again, the first one, July 2nd of 1967. And what's important also is to note that it was detected in 2 separate spacecraft. It wasn't just in one satellite, but in Vela 3 and Vela 4. Very, very unusual. And it wasn't unique. It was the first of 16 events like this detected between 1967 and 1972. So in 67, I was 2 years old. By 1972, I was 7. And anytime you see something in any given detector, maybe you can attribute it to a fluke in that detector, or maybe something individual that's going on in that spacecraft. But when you see something in 2 separate spacecraft that can be separated by 140,000 miles or more, they don't know about each other, and then you see 16 total events, you pretty well convince yourself that something is going on. And then the question is, what is it? Is this the Russians, or is this the Chinese, or is this the French? Or what are we seeing here? Are these human-induced events? Well, it was pretty well determined after a study of these 16 events that they were determined to be of non-terrestrial origin, meaning they aren't coming from the Earth or near Earth. And this is interesting to not only ask what do you know, but how do you know what you know? And with spacecraft that are separated by, let's say, 140,000 miles, they're in 70,000 mile orbits. The speed of light is a finite speed. And so what happens is these 2 satellites are separated in time. And much like you might see someone working on a roof in the distance, you watch the hammer go down, and then later on, the sound comes to you. And if you and your friend were, let's say, 100 meters apart, you would disagree on the time difference between the hammer coming down and when you heard the signal. You wouldn't hear the sound at the same time. And the same thing is true for these spacecraft. They might see the same event, but they don't agree on when they saw it. And because of the time difference, you can actually figure out a direction from which the event must have come and make some estimate about how far away it was. And so by seeing these events separately in these different spacecraft at different times, you pretty well can conclude that, well, they're not from around here, which presumably eliminates the Chinese and the Russians and other adversaries. And so these findings were declassified in 1973 with this paper that you see on the lower right-hand side, Observations of Gamma Ray Bursts of Cosmic Origins. APJL is APJ letters. That's the journal in which it was published. And suddenly we had a new physical phenomenon discovered in the universe, complete mystery, but discovered by accident by clandestine classified programs designed to monitor for clandestine nuclear explosions in space. So this makes the scientists really happy, like, woo, oh, new present. We can go open up some very beautiful science investigations. And they did. These devices were lofted into space. Some were lofted onto balloons, gamma ray detectors, to look for these bursts. Now, over a period of time, let's say from 1973 to, let's say, 1978, some progress was made and the events were begun to be characterized. So most of the light that you see, most of the X-rays or the gamma rays that you see coming from these events have energies between 50 and 300,000 electron volts. What do I mean by that? It's a little bit more intense than what your dentist would use for an X-ray of your teeth, a little bit higher energy than that. but not the kinds of things that you worry about, let's say, from severe nuclear decay, for example. But there is some very high energy emission that comes from these, up to 1.5 million electron volts. For the physicists or the physicist inclined in the room, if you take an electron and convert its rest mass entirely into energy through E equals mc squared, you get about 0.5 million electron volts. So 3 and 4 times the rest mass energy of an electron, those photons come out. But that's, most of the photons are in the X-ray and in the gamma ray. And their durations are interesting. You say, how long do these flashes last? Well, some were less than a second. Roughly maybe the equivalent of a flash bulb going off. Others lasted, over 100 seconds. So that's kind of interesting. Now, when we look at things in space, we can only ask really very few questions, surprisingly. One is, where is the location of the event on the sky? Where did it come from? How long did the event last? The fixed stars last billions of years. Nova and supernova may last days to months. How long did something last is a question that we can ask. How bright was the event? Was it dim? Was it bright? How bright was it compared to something else? Those are pretty much the basic questions of astronomy. And then you can get into questions about what is the spectrum, what color is it, and what is the energy distribution of the light that you're seeing. But these events were collected and you plotted on a map on the sky, and you can look here and you can say, well, do I see any pattern? Do I see anything like, let's say, the Milky Way, the band of the Milky Way galaxy, which would show up along this horizontal line? These are in galactic coordinates. You can see the events here, right? These are, each of these boxes that you see on the globe have equal area, and so should have roughly equal probability of a burst being located in there. And the answer was no. There's really no pattern to how they appear on the sky. And that's what I mean by red. The angular distribution on the sky is consistent with isotropy, which means basically it's random. Randomness dominates. And we can also ask questions about how bright the bursts are. And you might just have to take my word for it here. And we'll talk a little bit about this later. But for the bursts that we could see, the brightness distribution was consistent with the volume of space that we're sampling being uniformly filled. We can do some experiments, some thought experiments. So imagine standing, let's say, in the middle of the Astrodome, and I turn off all the lights, and the Astrodome is full of different kinds of light bulbs, 10-watt light bulbs, 100-watt light bulbs, 1,000-watt light bulbs. And we turn them on. I don't know how they're distributed throughout the Astrodome. But if the distribution is uniformly filled, in other words, the volume of the Astrodome is uniformly filled, I will get a brightness distribution that follows a -3/2 power law. We'll talk about this in a second, but basically the 3 comes from the fact that the volume is proportional to r cubed, the radius cubed, and the 2 comes from the fact that the brightness drops as 1 over r squared. And so you can see these data here along this plot that pretty much allows you to draw this -3/2 line through the brightness distribution. And so you're convinced at this point that whatever volume of space you happen to be sampling with your detectors out to wherever your detector can't see anymore because it's too insufficiently sensitive, that space is pretty much uniformly filled with gamma ray bursts. And the distribution in angle, or how are they distributed on the sky, is random, isotropic. And so we had to deal with what we see, but what we didn't see is when we detected a burst, we never saw any other optical, radio, or other identified counterpart. So it's not like you could look at that spot on the sky, let's say here where I've got my cursor and point a telescope, and see anything. It just wasn't there. So it's a very, very difficult problem, especially when you're dealing with limited observations and poor statistics and those kinds of things. But remember, it takes a long time to get a spacecraft built. It takes a lot of money to get a spacecraft built, and spacecraft tend to be small and lightweight, which when you're looking for collecting area and massive detectors to stop high energy photons works against you because the rocket equation is not friendly. So this is what I mean by angular isotropy. There aren't many things in the sky that are isotropically distributed. The planets are not distributed isotropically. They actually lie in the plane of the ecliptic. The solar system is constructed sort of like a frisbee, in the sense that most of the planets and moons and asteroid belt, they're all sort of in the plane of this frisbee. Comets are a slightly different thing. They have highly inclined orbits, but when you look up in the sky, for example, Jupiter never wanders near the North Pole. It is always in the ecliptic, as with all the other satellites. Now, if you've gone out to a state park, for example, or somewhere where the sky is dark, you can see that the stars that you can see with the naked eye are not distributed randomly, isotropically. They tend to cluster in a band called the Milky Way. Well, that's because the Milky Way itself is also shaped sort of like a large frisbee. We happen to be in the thickness of the frisbee, and so when we look out deep enough into space, we see a band. You've seen spiral galaxies, for example. X-ray pulsars, globular clusters, very, very few objects known to astronomy are isotropically distributed. And so when you see something in space that's isotropically distributed, usually it's a selection effect or some observational effect. So if I go outside, let's say in downtown Columbus, and I look around, I don't see the Milky Way. I just see kind of randomly distributed bright stars. Well, that's because I'm only seeing the bright ones. I'm generally also only seeing the nearby stars, and I'm not seeing deep enough into space to reveal the true distribution of how the stars are distributed on the sky. So that's a piece about angular isotropy. So when you look up in the sky, almost nothing is randomly or isotropically distributed. So that's the first piece. Where are they on the sky? Now let's look at how they're distributed in brightness. How many of each different brightness do I have? And we bin them up. We say, okay, I got so many that are between a brightness of 1 and 2, and then a brightness between 2 and 3, and 3 and 4, and 4 and 5. And we measure how many we see as a function of each brightness. And that looks like this. Here's this three halves curve again. I won't belabor the point. If you want to do the math, basically what you have to do is you have to assume some distribution of bursts as a function of distance from the Earth, which is an odd thing to think about because nothing in the sky is actually distributed as a function of how far away it is from the Earth. But the math allows you to do that. And then you also have to account for the fact that bursts come in different intrinsic sizes. Might be 10 watt, 100 watt, 1,000 watt bursts, each of which is different intrinsically. You add all those up and you integrate over both distance out to the distance you can see and the luminosity to come up with an expression of the number of bursts that you can see above a certain brightness. Now you think about this, eventually if I took a 100-watt light bulb and moved it further and further and further and further and further away from your eyes, eventually I could get far enough where your eye couldn't see it. It would just be too dim. The burst of the light bulb is still 100 watts. You just can't see it. So what you see here is this paper from Fishman et al. In 1978, and you can see Vela and IMP7 and some balloon flights and some other data that showed that for the bursts we could detect, it was sort of following this 3/2 power law. Dim bursts are over here on the left, bright bursts are over here on the right. Of course, bright bursts are more rare than dim bursts. You can think about that. Go out and look at the sky when you can see the Milky Way. There are many more faint stars than bright stars. But there's a hint here that this curve might start to roll over. And this was kind of intriguing. And it led to the discussion about why we would want to build a detector and what the theory was prior to the launch of the Gamma Ray Observatory in 1991. So between 73, when the events were made public, and 1991, when the Gamma Ray Observatory was launched, the consensus came to be that bursts were these moderately powerful nuclear explosions that were occurring on or near objects known as neutron stars in the Milky Way galaxy. A neutron star is basically the corpse, if you will, of an extremely massive star that has used up all its fuel, blown itself to bits. The core has collapsed into essentially a solid ball of neutrons, roughly the size of Manhattan Island. We see them in space. They tend to rotate very rapidly, and they emit X-rays and gamma rays, and so they're a natural energy source for these kinds of things. And the fact that we were seeing both a distribution of bursts that looked the same in all directions and a volume uniformly filled with bursts was explained by an observation effect that I've put here in a cartoon. So if you can imagine this green bar across the screen is the disk of the Milky Way galaxy, and we're kind of sitting here in the middle at the center of this light green sphere, which looks like a circle, but a sphere. And our detectors are small, so they can only see, out to about the edge of the circle. And if you look at the candidate burst sources throughout the galaxy, you'd say, oh, look, yeah, it kind of looks the same in all directions. I see the same number of bursts no matter which direction I look. And the volume of space that I am sampling with my detector seems to be uniformly filled. So we thought that's what we were looking at. And for 18 years to build research programs and get government money and graduate PhD students in astrophysics and all these kinds of things around this core, admittedly oversimplified hypothesis of what we're looking at, sets your expectation in a very interesting way for what you think you might see if you built a larger detector. Of course, a larger detector allows you to see deeper into space because you can detect fainter and farther bursts. And here's what you'd expect to see. You'd expect to see almost no bursts out at the edge because, well, there are very few, right? So you would expect to see a uniform distribution of bursts in space, volume space, until you got kind of to the edge. And then there wouldn't be very many weak bursts because they would be bursts that would be occupying these spaces out here. But there aren't any. So you would see that 3/2 curve roll over. And you would see an anisotropy, a change in how the bursts are distributed on the sky. If I looked along the plane of the galaxy where I'm moving my cursor, hopefully you can see it, I would expect to see a lot of bursts. If I look out of the plane of the galaxy, I would expect to see fewer bursts. This is exactly what happens when you go from downtown Columbus to, let's say, the John Glenn Astronomy State Park. Your eyes actually get to see deeper into space, not because you made your eyes bigger, but you lowered the noise. When your eyes can see deeper into space, the stars suddenly are no longer randomly distributed. There are fewer faint stars away from the disk of the galaxy than there are in the galaxy. So if you plot up the number of bright and dim stars you can see, there aren't as many dim stars as there would be if the sky were uniformly filled because you're seeing the disk of the galaxy. So that's a little bit about what we expected to find with the burst and transient source experiment on the Compton Gamma Ray Observatory. This is BATSE, BATSE, Burst and Transient Source Experiment. What you see here is this is up in the upper right-hand side. You see a line drawing of one of the 8 detectors that were flown on the spacecraft. And these are, sort of the size of a large television set or, bigger than a microwave, but smaller than a dorm refrigerator maybe. And it consists of a couple of detectors. There's a large area detector called large area because it's large, and then something called a spectroscopy detector, and I'll talk a little bit about how this works. These detectors were built by NASA Marshall Space Flight Center in cooperation with the University of Alabama in Huntsville, University of California, San Diego, as one of 4 instruments that flew on the 17,000-pound Gamma Ray Observatory. And you can see right here in the corner of the spacecraft, they're covered up with blankets. I'll try to get out of the way. There are 4 on the top. And then if I took the spacecraft and I were to rotate it so you could see the bottom, there would be 4 more. So a total of 8 that were put on the edges of the spacecraft to look out in every possible direction because you never know where the next burst is coming from. So each one of these has about 2,000 square centimeters of collecting area. It's roughly the size of a large wastebasket or basketball hoop, which is enormous compared to the small sort of styrofoam cup size detectors that were on there before. We put these on the spacecraft in the shape of an octahedron so that we would have full sky coverage. And if you think about a gamma ray burst comes plowing through the spacecraft, let's say in this picture from from this side over here, and it comes plowing through this way, these detectors over here are going to see the burst very well. These detectors over here are not going to see it very well. And so this is how we would get an idea of where on the sky the burst was coming from, just by looking at how bright it was in each of these 8 detectors. And you can precisely locate, precise meaning to about a degree. Now, that's great. However, by comparison, the moon is about a half a degree. And so if you go chase down a degree of sky with a decent telescope, it's an enormous haystack in which to try to find one of these needles. So while it's a great improvement over what we had before, it's not all that great from the perspective of really trying to follow up with a telescope. So my job when I got to NASA in 1987, these things were basically buckets of parts, bolts, photomultiplier tubes. And my first job at NASA was to serve as a principal instrument engineer to build this thing, to test it, and to calibrate it, and to get it ready for spaceflight. So how do you collect a gamma ray? This is a complicated chart, and I'll try to simplify it. It'll be in there for the record. But basically, you can't use a mirror to collect a gamma ray. It just doesn't work. The gamma ray goes right through it for the same reason that when you get an X-ray, it goes through your soft tissue. It doesn't propagate through your bones as much because it's dense, but you can't really use a mirror. So what we do in this case, the way the BATSE detectors work, the photon, which is here at the bottom, the gamma ray comes in, goes through an aluminum window. Aluminum window, yeah. Actually, the aluminum keeps the light out, but lets the gamma ray in. And it hits a crystal, a sodium iodide crystal. Sodium iodide is commonly found as a part of sea salt. It's partly also how you get your iodine and iodized salt. And what happens when the gamma ray hits that crystal is it can be stopped. But the crystal suffers excitation, and electrons in the lattice of the crystal are excited. And when they recombine, they give off blue UV light. And so the amount of light that the crystal gives off is related to the energy of the gamma ray that was deposited. So now you've changed the problem. You've stopped the gamma ray, you've collected its energy and transferred that energy into these photons of blue light that you now have to collect. So we allow that light to escape the crystal through a fused quartz window. We use quartz instead of regular glass because glass is not as transparent in the blue and ultraviolet. And we collect these blue UV photons with something called a photomultiplier tube. Basically, you put a high voltage across a bunch of metal plates. When the photon hits the metal plate, it releases an electron or a few electrons. Those electrons feel the voltage, they crash, they accelerate, they crash into a plate, they release more. And then you propagate this all the way up to an electrical signal that you can digest with a computer. So it's actually kind of a Rube Goldberg machine in how you have to collect information to get a gamma ray into a digital form that a computer can collect. And notice, we're not taking pictures. We're just counting gamma rays. How many gamma rays come into the detector per unit time? We cannot take a picture with this instrumentation. So it's a big counter, big collector. So here's a picture of the Compton Gamma Ray Observatory with some people, including a very nervous scientist right here. That's me. This is the first time we ever picked up the spacecraft. You notice we had to launch it sort of along its long axis, but we built it along its, it was sitting in that massive container. This is a building called R7A. It's out at TRW, now Northrop Grumman in Manhattan Beach, California. If you drive down the 405 near Los Angeles International Airport, just south, let's say you're on your way down to Long Beach or you're going to In-N-Out Burger in Huntington Beach, you'll pass this building along your right-hand side as you go south, and it's a huge spacecraft manufacturing facility. There were 4 instruments on board the spacecraft. You can see the kind of the 3 in the middle here. These are 3 gamma ray telescopes. The one in front called ASC, which was built by Naval Research Lab and Ball Aerospace in Colorado. The one in the middle is called EGRET. It was built by NASA's Goddard Space Flight Center. Sorry, this is Compton. EGRET is on the back end, built by NASA's Goddard Space Flight Center. In the middle is a Compton telescope. And that was built in Germany. It was a contribution from Germany and the European Space Agency to this. And as I said, it flew for 10 years. So we literally took the pieces of the burst and transient source experiment out to California, integrated them into the spacecraft, did full spacecraft testing. The spacecraft was put into a C-5 cargo airplane, flown from Los Angeles International Airport to the skid strip at Cape Canaveral Air Force Station in Florida, and we prepared it for launch at the Kennedy Space Center, and we were there for about a year and 4 months. This is what the launch looked like on April 5th, 1991. Again, the anniversary is today. This is the mission patch from the mission. You can see the swoosh here of the Gamma, indicating the primary payload being the Gamma Ray Observatory. 3 stars here, 7 stars here. This was called STS-37. And our crew was Commander Steve Nagel and pilot Ken Cameron. Mission specialist Linda Godwin, who was the first woman to receive a PhD in physics from the University of Missouri. Jay Apt, who's also a professional astrophysicist and an astronomer. And then Jerry Ross, who's a career astronaut. You see him here in the upper left-hand side, and he is the king of spacewalks, especially through the shuttle program. He was one of the most experienced spacewalkers in the entire shuttle program. And he's still alive and kicking, a graduate of Purdue University and a native of Indiana next door. So this was a really exciting day. It was pretty exciting also because the high gain antenna got stuck. It would not deploy. The solar arrays came out fine. The high gain antenna wouldn't come out. So we had to send the astronauts out into the payload bay to release the high gain antenna so that we could actually get data from the spacecraft, a little bit of an anomaly. But here you see it finally flying free from the payload bay of Atlantis. So we turned it on, and here's what we saw. We saw all kinds of gamma ray bursts. And if you'll notice the sort of fine detail in the time profiles here compared to what I showed before, and how bright the bursts are above the level of background from that small 1973 example that I showed before, you get a window into how much more sensitive the BATSE experiment was than anything else that had ever flown before. We started to see about 1 burst every day. We would come in the morning and see what the spacecraft had sent us from overnight, and we would open every day a big new sort of Christmas present a day to see what the universe had sent us. And you can see the variation in these burst profiles. No 2 bursts are alike. This one is amazing. It, boom, turns on, turns off, and it's all this variation, and go up and down, 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 boom. And then after about 40 seconds, it goes back to quiescent. Some of them are pretty short. This one's really bright, but it's not all that long, just a second or so. This one's really short and really intense. Some of them kind of rise up and are very smooth, very sort of soft profile in a sense, if I can use the word soft to describe it. This guy in the lower right, look at this guy, who's just complex as all get out. Now remember, these are like nuclear explosions that somehow we're turning on and off and on and off and on and off and on and off, and rapidly flickering or somehow these high energy gamma ray and X-ray explosions. There was a 4 order of magnitude, a factor of 10,000 span between the brightest and the dimmest bursts that we would see, and a factor of 10,000, 4 orders of magnitude in the range of duration. So, you know, anywhere from a few milliseconds to a few hundred seconds. We were able to confirm, indeed, most of the photons that we were seeing were between 50,000 and 300,000 electron volts. But there were no real, you know, sort of lines or features in the spectra. Just a real enigma. We would say if you've seen 1 burst, you've seen 1 burst, not you've seen them all, you've seen 1. No 2 were alike. The nomenclature here, in case you're wondering, 910503, this is 1991. May 3rd, 1991, July 11th, 1992, 920216, February 16B. We must have seen 2 that day. And on November 23rd of 92, we saw 2. This was the first one. So we would name these, and we started collecting them. And we started asking, how bright are they? And lo and behold, look at what we got. This is the brightness distribution as seen by BATSE. There are only 867 bursts in here. That's more bursts than were seen by every other detector up to that point. And you can see it's a little noisy at the bright end. There aren't very many bright bursts, but yes, the power law distribution here follows that expected 3/2 line that we had seen if we were sampling uniform space. uniformly filled space. And as I get to fainter and fainter bursts on the left, they start to roll over as we expected. Remember, I showed the cartoon where I had the disk of the galaxy here, and I said if we're seeing beyond the disk, there should be whole areas, volumes of space where there are no bursts, and they would be filled with weak bursts. So that's what we're seeing in this rollover of the curve, is just a deficit of weak bursts. If all the space we were sampling was full of bursts, this curve would continue on way up, and it would be way up here. And in fact, it's not. Several orders of magnitude. So that's good. That confirmed half of what we thought we were going to see, right? And so the other thing we thought we were going to see is that the bursts would clearly line up along the disk of the Milky Way galaxy. And that's what we saw. This is 2,704 gamma ray bursts, and it's as random as a random number generator could put them onto the sky. This was a conundrum beyond belief, because if you're seeing this, and your hypothesis is that the bursts are in the disk of the galaxy, you definitely should be seeing a huge cluster of bursts along the Milky Way, and that is not what we see. In fact, we were testing this distribution against sort of random number generators that computers could put in place. And if I took a coin and flipped it 100 times, I might get 53 heads and 47 tails. And you'd say, yeah, that's fair, but it's not 50-50, but it's fair. This distribution of bursts is more random than about 9 out of 10 computer-generated random throwing darts at the sky. Really, really a conundrum, and we had no idea what we were looking at. The angular distribution consistent with isotropy at a very high level. There's no clustering. They're not coming in splotches. There's no preferred direction. So it's not like they're sort of biased against the North Pole versus the South Pole. There's no repeaters. It's unlike anything except the most distant objects in the universe. Now I got to say, this map is 10 years of bursts. Remember, one burst per day. So it wasn't like this data came in all of a sudden. One per day, another one. After 2,700 days, okay, it looks like that. But in the early days, when we only had, let's say, 50 or 100 bursts, it was pretty scary because we could not figure out how to reconcile that and that. And so people wanted to reconcile it for us. Well, clearly, you people from Alabama who built this instrument, your instrument's not working, right? It's broken. You messed it up. You built this enormous spacecraft and somehow you screwed it up. Well, that could have been, because flashes of gamma rays, one of the first 5 events we saw actually were located to have come from the Earth, and that was a problem. Turns out it was a discovery, but we thought at first it was a problem. But solar flares were locating in the right place. We could see solar flares, and when we located them using the instrument location capability, lo and behold, solar flares came from the sun. The Crab pulsar was in the right place in the sky. So was Cygnus X1 and SCO X1 and other things. The flashes from the Earth turned out to be the first ever discovery of gamma rays coming out of the top of thunderstorms. So we can talk about that later, but that actually is, if you want to look at citations, among the most cited papers I happen to have a co-authorship on. But yeah, it was really surprising. No one ever thought thunderstorms made gamma rays. Other people said, well, I've been working on this for 18 years and I'm a pretty smart person and I got a PhD in astrophysics and 14 PhDs that I've graduated, and your instrument's working, but maybe there's some kind of systematic measurement effect, your locations aren't good enough, or the atmosphere of the Earth is scattering gamma rays into detectors, all kinds of things that we had to chase down. Or maybe there's really 50 different kinds of populations of gamma ray bursts and they're smearing things out. And then there was one camp, if you will, led by a scientist named Bohdan Paczynski. In my mind, he was really, really a fantastic guy. And you can see Heather Miller is mentioning me on some communication we're having, so pardon the interruption there. And he said, no, I think the bursts are not in the galaxy. I think they're cosmological. I think that's the best explanation for what we have. Now, okay, it fits the data, but the physicist goes, wait a minute. That requires something like quantitatively 10 to the 52 ergs per second. That's more energy than in 10 seconds than the sun emits in its entire 10 billion year lifetime. So from an observational standpoint, you might say that's Occam's razor, says that's the easiest explanation. But from a physics standpoint, that was really problematic. And so the debate raged. These are some of my colleagues that worked on this, from Krista Koveliotou at the lower left to Jan van Paradise at the upper right. And there's Bodan. He's since passed away. He's in the lower right-hand corner with his arms crossed. And it turns out we'll see whether he was right. I'll just mention Jerry Fishman here. Jerry was my very first boss at NASA. And for any of you young folks out there who are looking to get into science or actually anything else, it always pays to be kind to your boss. And in some ways, it always pays for your boss to be kind to you, because the oddity about Jerry Fishman, he was my first boss at NASA, and I was technically his last boss at NASA before he retired. So the world does come full circle, and I'm really blessed to have been able to work with great people like Jerry and Chip Meegan, and here's Don Lamb from University of Chicago, who was in the galactic camp. Bill Pachasis, who is at the University of Alabama, Huntsville. Dieter Hartmann, who's at Clemson University, came to the United States from Germany. This was really a global scientific mystery that went from sort of an interesting, curious corner of astrophysics to the problem. And the debate raged. But every time we collected a burst, you know, it tightened the constraints on how much anisotropy could be hidden. The more times I flip a coin, the higher and higher certainty I can give you that the coin is fair. And so we really were stuck. We needed a counterpart. We needed to be able to see it in some other way than just with BATSE. And in February of 1997, the breakthrough came. There was a small satellite called BEPOSAX, which was launched by an Italian-Dutch consortium. And this was benefited from knowing what BATSE had seen, and also said, okay, here's how we need to improve our instrument capability. So it had a little X-ray telescope on board and the ability to precisely locate a burst if it could see it, and the ability to slew the telescope to the position on the sky where it thought the burst came from. And so on February 28th of 1997, it saw a burst. Now, it couldn't see as many bursts as BATSE. It couldn't see as sensitive bursts as BATSE, but it could see bursts. And when it saw a burst, it could slew its telescope to where it thought it came from. And lo and behold, there you see this beautiful, bright X-ray splotch right there. And about 5 days later, it had clearly diminished in brightness. And if you were to look there today or 2 weeks later, there would be nothing. So this is part of the reason we couldn't see a burst in anything. You had to get on that location very quickly. And remember, I said a degree is too much sky for something like the Hubble Space Telescope to go after. But here you have just a few arc minutes. And so you can point precision telescopes at this spot in the sky and say, tell us what you see. So Hubble Space Telescope is one that we pointed, and this is what Hubble saw. Now, we're used to these huge pillars of creation and beautiful images from Hubble. That's because those things are pretty close. When Hubble has to go look at something this far away, this is the kind of picture that we get. It's not quite optically as beautiful and inspiring from maybe sort of a spiritual or metaphysical perspective, but from a science perspective, it's amazing. Because here is a Hubble image on 28th of February, 1997, and you see this splotch and this galaxy here. And then when we look again in on the 8th of March, it's gone. Here's the host galaxy, but the gamma ray burst counterpart is gone. This is what it looks like in living color. This is the gamma ray burst, and this is the rest of the galaxy in which it resides. So for the time the burst is going off, it's way more luminous, and therefore way brighter, than the entire galaxy it inhabits. Now, one of the things that Hubble was built to do is to measure what's called the redshift of objects in deep space. We know that the universe itself is expanding, and therefore the things in the universe appear to be receding away from us. And the speed at which they appear to be receding away is related to the distance. Things that are further away have a greater apparent recessional velocity. And much like when you hear a train whistle go by, you hear this pitch change. That's the Doppler shift of the sound. Hubble can measure the Doppler shift of the light, and it's redshifted, it's downshifted towards lower energies, just as it is in the sound with the train. And we can measure that redshift and then get a distance. And for this burst, the redshift was measured to be about 0.8, which is really, really, really far away. And this was the smoking gun that showed the bursts are not nearby, not in our galaxy, but are indeed cosmological and may indeed, occurring once per day, release more energy in a few seconds than the sun emits in its entire 10 billion year lifetime. So mystery sort of solved. One other piece I'll point out, my colleague Tom Koshut wrote his PhD dissertation on this. Chris Cavelliotu was another lead author on this. When we look at how long the bursts are, they tend to come in two separate lengths, a short population and a long population. Short being, on the order of a second, long on the order of about 30 seconds. Now, the angular and brightness distributions of these appear to be the same. The short bursts tend to have a higher proportion of high energy photons compared to the longer bursts. We might say they're a little bluer, harder spectra. The longer ones we now know, because we got pretty good at counterparts, are found in star-forming galaxies and are affiliated with broad-lined kinds of supernova in extremely massive stars. The shorter ones, it's less clear, but we have some evidence that these might be associated with neutron star mergers, or the mergers of neutron stars and black holes in older populations of stars. And that's important for a reason that will become apparent in a minute, because this mystery isn't over. It just got put on hold for a little while. And then all of a sudden, in a period of about a day and a half, the world came apart and got put back together again. So Gamma Ray Observatory, BATSE were followed by other spacecraft, SWIFT, which was launched in 2004, and the Fermi GBM, which was launched in 2008 and is still in operation. We continued to detect one burst per day from somewhere in the universe, and we have proven that these bursts are created at the end of the life of an extremely massive star. Maybe a star that was born in the early universe, about 25 or more times the mass of the sun, uses up all its fuel extremely rapidly, and then dissociates itself in a very highly energetic and really interesting event that produces a gamma ray burst. And when they go off, they rival the luminosity of the rest of the universe added together, which is just an amazing thing to think back to how originally we were looking for clandestine nuclear explosions from the Soviets or the Chinese. And we found nuclear explosions bigger and further away than you might have imagined. So here's kind of a baseball card, if you will, of back of a baseball card of some of the bursts that we've seen, dating back to 2008, where I say this is a typo here. This should be a 2. From BEPOSAX. The first redshift greater than 1, seen in December of '97. The closest burst to date, which was associated with first one associated with a supernova, was detected. Some of these are pretty interesting. I'll take a look at this one. 0803 19B, which is written there. 2008, most optically luminous event of any kind ever observed in the universe, the brightest optiglow of any gamma ray burst, and the first gamma ray burst ever that could possibly have been seen with the naked eye. This is a cosmological event, an event that occurs, billions of light years away, a star blowing itself to pieces. And someone could stand out underneath the night sky and look up and see it with your eyes. Pretty amazing, pretty amazing. Some of the most distant gamma ray bursts ever measured. And then at the bottom here, this interesting event, this gamma ray burst was seen, and one of the photons, one of the light particles came in at 31 billion electron volts, which means one particle of light has 3% of the kinetic energy of a mosquito in flight, which doesn't sound like a lot, but for a particle of light, that's a huge amount. And that light didn't come to the detector until almost a second after the gamma ray burst was detected. So all kinds of interesting mysteries here for scientists, physicists, condensed matter theorists, astronomers to put their thinking caps on and go forward. So there was one, or is at least one last interesting tidbit to share, which is I think where the direction of all of astronomy and astrophysics are going. And that is with the detection of gravitational waves. Now you're probably familiar with the fact that in 2016, scientists announced that for the first time, they had detected gravitational radiation. This is a completely new window on the universe. It's not detecting particles. It's not detecting light of any kind. It's detecting gravitational waves, which were detected likely from a very massive merger of two black holes. So, interestingly enough, what we've plotted here is count rates from the Fermi glassed gamma ray burst monitor instrument as a function of time. And 0 here is aligned to the time of the gravitational wave detection made by LIGO, which is in both Louisiana and in Washington State. These two detectors detected this gravitational radiation at the same time. And curiously enough, in the Fermi data, there is an untriggered gamma ray burst about 0.4 of a second after the gravitational wave detection. Now, it's kind of interesting, but I'm not sure you could write your stake a career on it. It might be a coincidence. It was untriggered, so therefore it's weak. The burst detector could see it, but it did not set the threshold to say, oh yeah, for sure that's a burst. Now we expect the gravitational radiation to be weak and therefore nearby because the detector isn't that sensitive. It should be detecting nearby events, not distant faint events. Why is this burst so weak? Good question. It's very poor localization because it's weak, but it's not inconsistent with the detection direction for which people thought the gravitational wave detection is. So you're like, well, interesting. What do I do with this? Sort of the cruel universe theory that it hands you intriguing data, but nothing that you could really draw any real concrete conclusions from. So people were sort of just kind of scratching their heads and thinking, well, gee, what is this? I see the burst. We know we see gravitational waves at the same time, sort of, maybe not. What are you going to do, right? And the answer is just hang tight. The universe is always sending stuff to you. These bursts have been on their way to the Earth since before the Earth was formed. So just hang in there. Maybe we'll see something else. And we'll be able to say something about gamma ray bursts and gravitational waves? And the answer turns out to be yes. Now, I'm going to totally skip through the excitement here because it's hard to convey. August 17th of 2017, so coming up on 2.5 years ago, LIGO, the gamma ray detector, or the gravitational wave detector, I'll show you in the upper left hand here. This is what their detection looks like. And what you're hearing is me making a sound sort of simulating the frequency of gravitational radiation that is detected as these two objects spiral in on each other and ultimately annihilate. So this is the gravitational wave detector, and right here is the Fermi GBM gamma ray burst detector. Boom, gamma ray burst. This is a different spacecraft down here called Integral, and you can see not very sensitive, but clearly something interesting in that detector, right? And then we start to put on in time also all of these other observatories, because what happens is as soon as LIGO sees a burst, it sends out a gravity wave burst, it sends out immediate notifications to anybody and everybody saying, hey, if you've got an instrument, point it here because we just saw gravitational wave detection. Well, the gamma ray burst detectors were already on station, X-ray detectors following up. Here you see optical counterparts from no fewer than 6 different telescopes on the ground. There's the optical counterpart, there's the galaxy, and you see it all across the board, followed up with X-ray observations from Chandra, radio observations from the Very Large Array. This one cosmic, celestial, and cosmological event was seen in gamma rays, X-rays, UV, optical, infrared, radio, and gravity waves. Now, it was short and relatively weak, but it is a smoking gun unlike anything else, in my view, in the history of astrophysics, bar none, bar none, bar none. And you can see here the paper from October of 2017. Look at the list. This is just amazing to me. Usually you see a couple of authors, and look at the list, not of authors, but of collaborations that worked together. And if you ever are, if you're a fan of Slack, the collaborative workspace Slack, you can go read the Slack channel. From the time the LIGO community detected the gravity wave through the entire collaboration. This is CN matter for the full list of others. I think there's 5,000 people on this paper. And it really points to the nature of how science is done today. There are no first single author, I wrote a whole paper by myself kinds of conversations going on. And to me, this is the future of astronomy and astrophysics. And from a gamma ray burst perspective, starting with an accident, we plodded along for a long time with insensitive detectors and 18 years of a theory that did not turn out to be true. And in about 24 to 36 hours, we went from the first ever observation of a neutron star merger produced radiation across the spectrum. We got to see it all over the place. And this literally is one of the most important astronomical observations of your or my lifetime. Some highlights from this one burst. We know the host galaxy, New General Catalog 4993. The very first time electromagnetic and gravitational wave radiation was detected from the same source. It happens to be very, very close, at least on a cosmological distance scale. It's only about 40 million parsecs away. A parsec is about 3.2 light years, so maybe 120, 150 million light years away. The redshift is therefore very low, and it is one of the closest gamma ray bursts to date. I will point out this paper, which was authored in part by Bohdan Paczynski in 1998, that predicted what the light curve, the power of the light curve should look like, how it should decay away. Here we are in 2017 for this burst. That paper literally kind of sat on the shelf as a prediction for 20 years. 20 years later, here comes the event, and lo and behold, Bohdan was not only right about the geometry in space, but also right about some of the physics behind what powers it. Now, interestingly enough for me, and what's tantalizing, and there are explanations for this, but none of them really make me feel good. If this burst is so close, why is it so faint? Because close bursts at this distance should be really, really bright in gamma rays, and it's a piddly little burst in gamma rays. It's the most important one we've ever seen, but it certainly isn't remarkable from the level of how bright it is. So where are we going? Well, I think you're seeing the growth and the emerging interdependence of astronomers and astrophysicists who deal in photons. They collect light, or they collect particles, they collect high energy cosmic rays and gravitational radiation. And this really is the beginning of an entire new epoch in our ability to understand, explore, and observe the night sky. I think you're going to see gamma ray burst detectors and other high energy detectors routinely placed aboard commercial spaceflight vehicles like Dream Chaser, SpaceX perhaps, on our lunar base if we ever get one, on the Lunar Gateway. These are devices that will help us further explore the high energy universe. They also have extreme practical applications for things like monitoring the radiation environment for astronauts, studying solar flares and high energy particles that zip through the Earth's magnetosphere and other things. You're going to see a transformation of lunar gamma ray observatory opportunities in terms of on orbit around the moon in the surface. The bottom line is that we're going to go as far as our integration of science and engineering can take us, and also as far as our imaginations can go. So this kind of concludes the on-screen portion of the slides. I hope it's been informative. We're going to switch over, and so if it looks like I changed my clothes, it's because we're going from the recorded portion of the Zoom to the live portion. I really, really appreciate you taking the time to be with me and with us today. It's really a great thing that the community puts together from the College of Arts and Sciences, Physics and Astronomy, and today I'm pleased to join you from the College of Engineering. Ohio State's legacy and history, in my view, in astronomy and in astrophysics is one of the best of any universities in the world, not just in the United States, bar none. We have one of the most amazing physics and astronomy education research departments that you will find anywhere on the planet. It's really, really blessed with very special people who are extremely competent and leaders in the field. And so when you think Ohio State University, yes, we can think go Bucks, we can think Saturdays at the Oval, but we can also think equally highly of our high quality astronomy and astrophysics team that we have, students, faculty, and research staff. So thank you. I'm going to turn off the recording and we will be happy now to answer any questions that you may have.